Consider the following first-order initial value problem. Y prime equal to a function of x and y, h of x and y. And y at x naught is equal to y naught, where h and h sub y, the partial derivative with respect to y of h, are continuous on the rectangle x naught minus a plus x naught plus a, closed interval, cross another closed interval, y naught minus b, and y naught plus b. This rectangle is basically the rectangle that the length of it starts from x naught minus a to x naught plus a, and the height of it starts at y naught minus b to y naught plus b. We want to define a recursive formula for a sequence of functions called Pickard's iterates that increasingly approximate the solution to this equation as the recursion is applied repeatedly within this rectangle. To find this recursive relation, we integrate both sides of that equation from x naught to x. That is, integral from x naught to x, y prime of t dt is going to be equal to integral from x naught to x, h of t and y of t dt. Notice that we switch the integrands to a dummy variable from x to t. By fundamental theorem of calculus, the left-hand side is going to be equal to y of x minus y of x naught, which according to the initial value is equal to y naught. And the right-hand side we keep as it is. Rewrite this again. Solving for y is going to be y equal to y naught plus integral from x naught to x of h of t and y of t dt. This equation is the recursive relation that defines the Pickard iteration. To define Pickard iteration, we start with the zeroth function, f naught of x, to be the constant function y naught. Notice that this function is within the rectangular region we mentioned and passes through the initial points x naught and y naught. We define f1 of x using the iteration, which is going to be y naught plus integral from x naught to x of h of t and f naught of t. We define f2 of x using f1, that would be y0 or y naught plus integral from x naught to x of h of t and f1 of t dt. Now you can see the relation. So in general, we're going to define f sub n plus 1 of x to be y naught plus integral from x naught to x of h of t and f of n of t dt for n equal to 0, 1, 2, and so on. Let's give a few examples. First one, consider the initial value problem, y prime equal to y at 0 equal to 1. Let's pick the zeroth iterate to be f naught of x equal to 1. Then f1 of x is equal to y naught plus integral from x naught to x of 1 dt. And y1 because h of t and f naught of t is equal to f naught of t in this case. That's the h of x and y. And therefore, because f naught is 1, this is going to be integral from 0 to x of 1 dt, which is equal to 1 plus x. So f f2 of x is going to be y naught plus integral from 0 to x of 1 plus t, which is h of t and f1 of t, or f1 of t, and that is going to be 1 plus x squared divided by 2. We continue this way, and you can already see that these are Taylor polynomials for e to the x, and essentially f sub n of x converges to e to the x as the iteration goes through infinitely many times. Notice that the solution to this equation, which is both separable and linear, is e to the power x and is defined from negative infinity to infinity. So there's no limit in the domain of the Picard iterates at this point. E to the x is graphed here by the pink dashed line. Visually, we can look at the Picard's iterates getting closer and closer to that as we get more and more iteration done. The new iterate is closer and closer to the e to the x. And this is the same way that you would see that Taylor polynomials for e to the x converge to the e to the x, or the series e to the x. Let's do another example. This example also satisfies the conditions of the existence and uniqueness theorem. Namely, here is h of x and y, which is continuous everywhere, and its partial derivative with respect to y is continuous everywhere. So you can choose any size closed and bounded rectangle around 0 and 1, which is the initial value. So consider this initial value problem, y prime equal to y squared, y of 0 equal to 1. And so if you Picard iterates, starting from f naught of x equal to 1, f1 of x equal to y naught plus integral from x naught to x of 1 dt, which 1 is h of t and f naught of t, which is f naught of t to power 2, which f naught of t was actually 1. This is equal to 1 plus x. f2 of x is again y naught plus integral from 0 to x of h of t and f1 of t, which is going to be equal to f1 of t to power 2, or 1 plus t to power 2 dt. And it's equal to 2/3 plus x plus 1 quantity to power 3 divided by 3. We're going to approximate 1 over 1 minus x when x is less than 1. This is actually the solution. This is the solution to this differential equation. You can use the separable method to solve. And notice, even though, as we said, the h and h sub y were continuous everywhere, the solution was limited to smaller domain. Again, for this ODE, with that initial value, the solution is going to be y equal to 1 over quantity 1 minus x, and the solution goes through 0 and 1. And there is a unique solution, actually, for that initial value. Now, different iterates for this solution, or for this differential equation, is going to approximate this solution better and better. Last, the solution y equal to 1 over 1 minus x has a vertical asymptote at x equal to 1, and it seems that iterates are trying to follow that asymptote and grow as fast as that when the n iteration gets closer to infinity. Consider the initial value problem, y prime equal to third root of y squared, y at 0 equal to 0. This ODE does not satisfy the conditions of the uniqueness and existence theorem. And why is that? Because if this is h, if the third root of h squared is h of x and y, then h sub y, which is the partial derivative of h with respect to y, at 0 and 0, is going to not exist. So we cannot define a rectangular region around the initial value. Now let's see what happens with the Pickard iteration. Let's assume the f naught is 0, then f1 of x is going to be also 0 function. f2 of x is going to also be the 0 function. And it just seems that Pickard iterates are going to converge to 0 function very nicely. And that actually is a solution to this differential equation. We know that through solving the differential equations using separable method, there is another solution to this differential equation. So the solution is not unique. And that comes with the fact that the conditions are not met. We guess that there might be more than one solution. The discussion that this could be infinitely many solutions comes in another video. Fun fact, if we start with the same ODE and same initial value, and the solution that is related to the separable method is shown by this graph in dashed pink. And if we change the initial f naught, Pickard iterate, to f naught of x equal to x instead of what we had before, notice that f naught of x equal to x or y equal to x goes through the initial point. Then the Pickard iterates get closer and closer to the pink line that is the separable solution. Our goal is to show that Pickard iterates become closer to one another under the conditions of the theorem. To make this statement precise, we first need to define what it means for two functions to be close. In other words, we need to define a distance between functions. There are several ways to define distance between functions. Such distance functions are called metrics. We will use a metric that is appropriate for our setting. A metric must satisfy the following properties. Positivity. The distance between two functions is non-negative. So if d is the distance function, d of f and g is bigger than equal to 0. Identity. The distance between a function and itself is 0. The d of f and f equal to 0. Symmetry. The distance is unchanged when the order of function is reversed. So d of f and g is equal to d of g and f. Triangle inequality. For three functions f of f and g and h, d of f and g is less than equal to d of f and h plus d of h and g. For any s less than equal to a, and for any continuous function f and g defined on x naught minus s and x naught plus s, we define the metric to be d of f and g is equal to the maximum of the positive distance between f of x and g of x for every x in the interval, closed interval, x naught minus s and x naught plus s. Notice that all Pickard's iterates are continuous, and continuous functions attain their maximum and minimum value on a closed interval. The distance function is well defined over x naught minus s and x naught plus s closed interval. The value of s must be chosen so that all Pickard iterates fn and in n, in a natural number n, remain inside the rectangle. So we'll show for what value of s that's true. However, showing that this distance function here satisfies all four properties and therefore is well defined is left for the viewer. Next, we will show that for a correct value of s, the distance between successive Pickard iterates become arbitrarily small. Then we will prove that given any epsilon bigger than 0, there exists an integer, capital N2, such that distance of f sub n and f sub m is less than epsilon whenever both indices m and n are bigger than capital N2. This is exactly the definition of Cauchy sequence. That means that the Pickard iteration. We will show that under the conditions of the theorem, Pickard iterations are Cauchy and they converge. That is, we will show that the pointwise limit of the Pickard iterations is continuous and satisfies the integral form of the initial value problem. Consequently, this limit is a solution to the original initial value problem. To be able to use the extreme value theorems, we want to show all Pickard iterations are inside the rectangle, the closed rectangle. We want to have an m defined as the maximum of absolute value of h of x and y, such that x and y is in the rectangle, closed interval, x naught minus a and x naught plus a, times y naught minus b and y naught plus b. This is possible because the closed interval x naught minus a and x naught plus a times closed interval y naught minus b and y naught plus b is closed and bounded rectangle in R2. So that makes this maximum possible by extreme value theorem. Recall for n bigger than 0, the positive distance between f sub n of x and y naught is equal to the positive absolute value of integral from x naught to x, h of t, and f sub n minus 1 of t dt. This is just rewriting the recursive equation and putting absolute value on both sides. We show by induction that for some s less than minimum of b over m and little a, and for all x in closed interval x naught minus s and x naught plus s, the distance between f n of x and y naught, the positive distance between them, is less than equal to b. Base case, f naught of x is equal to constant function y naught. That implies f naught of x minus y naught is equal to 0, less than b, for all x in closed interval x naught minus s and x naught plus s. Induction hypothesis for case n minus 1, absolute value of f sub n minus 1 of x minus y naught is less than equal to b for all x in that closed interval. Induction steps. Absolute value of f sub n of x minus y naught is equal to the absolute value of x naught of integral from x naught to x of h of t and f sub n minus 1 of t dt. That is less than equal to absolute value of integral from x naught to x of absolute value of h of t and f sub n minus 1 of t dt, which by definition of m is going to be smaller or equal to absolute value of the integral from x naught to x of m dt, which is equal to m times absolute value of x minus x naught. Because x is in this interval x naught minus s and x naught plus s, closed interval that, we know that s is less than b over m. We know that x minus x naught, absolute value of that, is less than equal to s, less than equal to b over m. So the entire thing becomes less than this entire thing. The absolute value of f sub n of x minus y naught is less than equal to b. That means that, which in turn means that f sub n of x is in this interval, y naught minus b and y naught plus b, closed interval. This means that the values of all Picard iterations are within that rectangular region when we shrink the x values to x naught minus s and x naught plus. A Cauchy property. We want to apply the mean value theorem to the function h of x and dot, which means that it's going to be a function of the second variable. So we fix x, so h of x and dot is going to be a function of the second variable only, and apply the mean value theorem to the function g of y equal to h of x and y. Basically, if you're fixing x, your domain becomes this line, vertical line above x. Now, by mean value theorem, h of x and f sub n of x minus h of x and f sub n minus 1 of x is equal to the h sub y of x and k times quantity f sub n of x minus f sub n minus 1 of x. The first one, the h of x and f sub n of x is g of fn of x. H of x and fn minus 1 of x is g of fn minus 1 of x. H sub y of x and k is g sub y of k. And k is between f sub n of x and f sub n minus 1 of x. So k is on this line between f n minus 1 of x and f n of x. Now, absolute value of h sub y of x and y, the partial respect to y of h at x and y, is less than equal to some value L for all x and y in the rectangle x naught minus a and x naught plus a times y naught minus b and y naught plus b. Why? Because h sub y is continuous on this rectangle, and it's a closed rectangle, closed and bounded rectangle. It attains its maximum. Therefore, the absolute value of h of x and fn of x minus h of x and fn minus 1 of x is less than equal to L times absolute value of fn of x minus fn minus 1 of x. This is by replacing h sub y in that equation, h sub y of x and k, with its maximum, so the equation becomes inequality. And this is true in the restricted x naught minus s and x naught plus a times y naught minus b and y naught plus b. Consecutive Picard iterations get closer. Let's start with absolute value of fn plus 1 of x minus fn of x, which is equal to the absolute value of integral from x naught to x of h of t and fn of t minus h of t and fn minus 1 of t dt. This is less than equal to if we also add an absolute value to the integrand of the integral, then that is less than equal to the absolute value of integral from x naught to x of L times absolute value of fn of t minus fn minus 1 of t dt. This is according to the last results from the last page, because this absolute value integrand in the line above is less than the integrand in the line below, according to that result. Now, this is less than equal to L times absolute value of fn of x minus fn minus 1 of x times absolute value of x minus x naught. If we also assume that the s that we chose for the length of the rectangle is also less than 1 over 2L, then we can say that this entire thing is less than equal to L times fn of x minus fn minus 1 of x, absolute value of that, times 1 over 2L. Now, L's simplify, and you get 1/2 of absolute value of fn of x minus fn minus 1 of x. So for each x, the difference in the consecutive Picard iterates gets smaller. Now, if x star is a value such that the distance of fn plus 1 and fn is equal to absolute value of fn plus 1 at x star minus fn at x star, then we can say that fn plus 1 x star minus fn x star absolute value of this quantity is less than equal to 1/2 of absolute value of fn of x star minus fn minus 1 of x star. Absolute value of fn plus 1 of x star minus fn of x star is less than 1/2 of absolute value of fn of x star minus fn minus 1 of x star. This absolute value, the latest absolute value, is less than 1/2 of d, less than equal 1/2 of d of fn and fn minus 1. Therefore, the distance between fn plus 1 and fn is going to be less than equal to 1/2 of d of fn and fn minus 1. Now we want to use the fact about consecutive Picard iterations to show that Picard iterations get arbitrarily close. That is, we want to show that for every epsilon bigger than 0, there exists an integer capital N such that the distance between f sub n and f sub m is less than epsilon whenever m and n is bigger than capital N. Repeatedly applying the previous estimate gives the distance of f sub I and f sub I plus 1 is less than equal to 1 over 2 to power I, the distance between f0 and f1. By triangular inequality, d of fn and fm is less than equal to the sum I equal to n all the way to m minus 1 of d f sub I and f sub I plus 1. These are the consecutive ones. Now, to make the computation more familiar, we're going to add this infinite sum to the old sum. And that makes it, because this is infinite sum of all positive values, it makes the old sum bigger. Again, we want it a little bit more bigger by, instead of starting at little n, we're going to start at capital N. And so now we have this infinite sum starting at capital N to infinity of fd of fi and fi plus 1. That is going to be bigger than d of fn and fn fm. So what next? That is less than equal to d of f subcapital N and d of f subcapital N plus 1 times the sum starting at n to infinity of 1 over 2 to power I. This is left to the reader to show that part. And that is 1 over 2 to power n minus 1 times the d of f0 and f1. It follows that for every epsilon bigger than 0, there exists an integer n such that d of fn and fm is less than epsilon whenever m and n are bigger than capital N. Therefore, the sequence of Picard iterations is a Cauchy sequence. Limits of the Picard iterations. Define f of x to be equal to limit of f sub n of x as n goes to infinity for all x in x0 minus s and x0 plus s. So you're pointwise defining f of x through the Picard iterations. We're hoping to show continuity of this function, that is the pointwise limit of f sub n's using epsilon and delta. So instead, let's look at this picture. In this picture, you can see Picard iterations and f is the pointwise limit of these Picard iterations. Now, let's look at the point P in the domain, which is x0 minus s and x0 plus s inside the domain, an open interval. And then, so P and f of P is on the graph of the limit function. But because this limit function is a pointwise limit, uh, for any interval f of p minus epsilon fifth and f of p plus epsilon fifth, it contains basically the tail of the uh, Picard iterates, which means that for there exists a capital N1 such that f I of p is inside this interval for all I bigger than n1. Now let's fix in n such that n is bigger than n1 and it's also bigger than n2, where n2 ensures the Cauchy property. That is the distance between f n and f sub I uh, is going to be less than epsilon fifth uh, whenever I and n are bigger than n2. Now, because f sub n, the fixed one, is continuous at p, we can find a delta interval around p minus delta and p plus delta, such that f sub n, basically the difference, positive difference between f sub n at p and f sub n at x, is going to be less than epsilon fifth for every x in this interval. Now, take any point x in this interval and find the x and f of x, which is the f is the limit function, right above here. So what happens to this x and f of x? I know that f of x minus epsilon fifth and f of x plus epsilon fifth contains the basically the tail end of this Picard iterations. What tail end? Let's say it's for some capital M of x. It contains all of them. And so what is happening here? Now, for every x in that p minus delta, the delta that we chose, depending on that n, and p plus delta, in choose any I bigger than max of n1, n2, and m sub x, then absolute value of f of p minus fi of p is less than epsilon fifth, and absolute value of fi of p minus fn of p is less than epsilon fifth. This is because of the n1 and n2, and also absolute value of fn of x minus fi of x is less than epsilon fifth because of n2, and then absolute value of fn of p minus fn of x is less than epsilon fifth. In this one is just because of the continuity of fn. Finally, the absolute value of fi of x minus f of x is less than epsilon fifth because of m sub x. So when you sum all of these, they are less than 5 epsilon fifth, which is epsilon, and they are also bitriangular inequality. If you go pair by pair, they are bigger than equal to absolute value of f of p minus f of x. So what does this? Therefore, absolute value of f of p minus f of x is less than epsilon whenever the absolute value of x minus p is less than delta, which is the continuity for the limit function f. I have to add that we could have used the uniform convergence in this case. Some theorems are out there to show the continuity. The limit of the sequence is a solution. This uniform convergence that we didn't define, then that can be shown through Arzela-Scully theorem for Picard iterations allows us to make sure that the pointwise limit of Picard iterations is actually a limit. That function is a limit of the functions. So we define limits as n goes to infinity of the fn, these are the Picard iterates, is equal to f, which is the pointwise convergence of the Picard iterations, to mean that the distance between f and fn goes to 0 as n goes to infinity. This is again not exact definition, it's just the feeling of it. So using this definition, we have limits as n goes to infinity of f n plus 1 is equal to, this is the very first definition, it's going to be limits of n goes to infinity of y0 plus limit n goes to infinity of the integral from x0 to x of h of t and fn of t dt. Of course, limit of y0 is going to be just y0. And then we can actually, through all these conditions that we say, we can bring the limit inside the integral. In this limit, if you remember, which is by definition, we're going to go is equal to fn. And so bringing the limit inside and inside of h, we end up with the integral from x0 to x of h of t and f of t dt. Thus, f satisfies the integral form of the initial value problem and is therefore a solution to original initial value problem. Yay! This completes the proof of the existence part of the theorem. Although we skipped a few things, but we got there. To show uniqueness, suppose that G is another solution. Then G has to satisfy the integral form of the ODE. That is, G of x should be equal to y0 plus integral from x0 to x of h of t and g of t dt. Earlier, we showed that for sufficiently small rectangle, namely that x0 minus s and x0 plus s cross y0 minus b and y0 plus b, the distance between y0 plus integral from x0 to x of h of t and g of t dt and y0 plus x0 integral from x0 to x of h of t and f of t dt is less than 1/2 of the distance between g and f. However, since f and g are both solutions, the left-hand side is equal to the d of g and f. Therefore, d of g and f is going to be less than 1/2 of d of g and f, which is impossible unless d of g and f is equal to 0. That is, g is equal to f. That completes the proof of uniqueness.